So a vector, far as you guys are concerned, is an object that has a magnitude and direction. This pencil, for instance, could represent a vector. If I had a mess load of them, or if I had access to make a bunch of them, I could say I'm on a scale such that the end from here to here is exactly 10.2 newtons, say. And then I'd measure that, say, in centimeters, and I'd write down somewhere 12.82 centimeters is equal to 10.4 newtons on paper. That's now a scale factor that allows you to draw scaled and correctly scaled vectors. Okay. The other thing about the vector is, in addition to having length, it has to have a very specific direction. So if you called, say, horizontal the x-axis and vertical the y-axis, then this might in fact be a 30-degree angle. And I can take this vector and move it around anywhere I want, as long as I don't stretch it, compress it, or twist it. Okay, later on you'll study vector spaces, and there's strict rules about moving a vector from A to B to C or whatever. But right now we're just dealing with vectors that are floating in space, not vector fields. So you are completely allowed to take whatever you're using to represent a vector. You're allowed to move that around to make it convenient. You just got to make sure you don't change which direction it's pointing, and you don't change how long it is or how short it is. Okay, because that's the magnitude and direction. Now, there's other rules associated with these vectors, like, for instance, if I switch from one coordinate system to another, there's a very specific set of rules that we use to make that coordinate switch. And you don't need to know those. You won't need to know those unless you take calculus on manifolds. But that's just like another rule. The good news is, all you need to think right now is, eventually I'm going to deal with fields, so that'll come up. But right now I just need to think of vectors as being represented by arrows, the length of which via a scale can give me the magnitude of the vector, and the angle of which, using a protractor, can give me the direction. For instance, you might call east the X direction, you might call north the Y direction, and then of course straight up and down would be straight up from the ground would be altitude, and that would be your Z axis. So those are all different ways you can do it. You need a lot of experience adding vectors. Hopefully you did quite a few in your pre-calculus class. You're going to do a lot more in chapter 3, 4, 5, 6. And what I recommend, as you'll look in your modules, you'll see there's one particular video link called The World's Greatest Vector Addition Problem. I named it that. Okay. I don't really think it's necessarily the world's greatest, but in some sense it is, because I took the time to put a lot of vectors in it. And all the vectors sort of tick off all the possible scenarios. You know, I wanted to make sure some vectors have X component that's negative and Y components that's positive. Some I wanted opposite to that. Some I wanted to have both negatives. Some I wanted to have both positives. And not only that, I specified them in every possible way that I would be likely to specify a vector. So for instance, when I'm talking to you about a vector, I could say there's a vector that's 50 newtons and it acts 5 degrees north of east. That's one way I could specify a vector. 50 newtons, 5 degrees north of east. I could also specify a vector to say there's a vector B, which equals 5 meters I hat plus 3 meters J hat plus 2 meters K hat. That's another way I could do it. I could say that a vector has a magnitude of 1,000 newtons east southeast. Well, if I just say east southeast, that means you're supposed to split between southeast, which would be a pure 45-degree angle between south and east. And since I said south southeast, I'd cut the 45 in half and have it closer to the south than to the south southeast. Okay. So all of those are different things. What I'm trying to get you to do though is never, ever, ever use negative angles or negative dimensions for your vectors. What you're going to do is on a case-by-case basis, you will draw the vector that you're going to, or at least picture it in your mind, the vector that you're going to work with. And then you're going to imagine it having a component that's parallel or anti-parallel to the x-axis, having another component that's parallel or anti-parallel to the y-axis, and maybe even a third component that's parallel or anti-parallel to the z-axis. And what you're going to do is say, okay, well, I have the magnitude of this vector, and I know the angle that's smallest from the vector to the nearest axis. So I'm going to take the cosine and the sine of that angle and multiply it by the magnitude, and think about the three-dimensional triangle, as well as I use some old horse came a hopping through my alley. But think about that mnemonic or your definitions of sine, cosine, and tangent, and figure out which one's the x component, which one's the y component, and then remember to put the sign on it. Okay, so let's get started talking about vectors a little bit. So first off, I'm going to say there exists a vector A. And here's where you probably want to see my stuff that I'm writing. And I am just so smart that I came up with it on my own this time. I feel like we've passed something now, like I'm a teacher now or something. Okay, so here's our vector A. Okay, now I can pick that vector up and move it anywhere I want to, but the main thing is I'm going to draw a different color and I'm going to do this. The main thing is that I do not want to change this angle theta, nor do I want to change this length, which can be represented by just A, or it can be represented by A with a vector symbol over it in between absolute value bars. Okay. Now, if I called this the x-axis and I called this the y-axis, then you could see this actually casts two shadows. They're both in the positive direction. So I'm going to say, here's one. This one's called a sub y because it's parallel or anti-parallel to the y-axis. And then there's another one, and I normally use the word shadow, so that's kind of a nice way of thinking about it. Here's the shadow of A on the x-axis. And of course, that's also parallel or anti-parallel to the x-axis. In this case, you can see that both AY and AX are positive. So let's say, just for argument's sake, that A is actually equal to 50.0 meters. Okay. And let's say, for instance, that this angle theta is 53.13 degrees. Okay. Now that I've stated a magnitude and direction, I can actually put a vector over top of that, and it's now a vector quantity. You're not supposed to have a vector equal to something that's not a vector, no more than you're supposed to have, apples equal to oranges. So what we can see is we have a right triangle. So let's look at that right triangle for a second. It looks like that right triangle is maybe this. where this is 50.0 meters and this is 53.13 degrees. Okay. And this is why I tell you guys, go ahead and write sine, go ahead and write cosine. And then the more familiar you get with it, then by all means, you can jump right into the components. But what I'm going to do is I'm going to say sine of theta is equal to opposite over hypotenuse. And I see that the opposite side, of course, is a sub y, and the hypotenuse is just a. Okay. So in other words, this red triangle is supposed to represent the green one I drew a second ago. That's why it's okay to call that AY. And this one's called AX. I don't know what that noise was, but it was pretty loud. So if you actually want to know, AY or AX, what I'm telling you guys to do initially is go ahead and take the time and write out what the sine of theta is and write out what the cosine of theta is. So cosine is adjacent over hypotenuse. Another way of saying adjacent, because that, at least when I was in high school and probably even my first year of college, I didn't really understand what the word adjacent meant. What I've decided to tell people is it means touching. Okay. So if the side is touching the angle, it either is the hypotenuse or it is the adjacent side. And remember, in a right triangle, the little right symbol acts like an arrow pointing to the hypotenuse, so you never have that problem. So in this case, the adjacent side is AX, and the hypotenuse, of course, is just the A, which we know is 50 meters. So from that, I can tell you that AY is actually equal to 50.0 meters times the sine of 53.13 degrees. Well, y'all might already recognize this number. Hopefully you do, or these numbers on this triangle. But basically, I force a positive because I know that it was its x component and its y component are both in the positive direction. So I force that sign. And when I multiply 50 times the sine of 53.13, I actually get 40.0 meters. Similarly, a sub x becomes 50.0 meters times cosine 53.13 degrees. In this case, it's also positive, and it turns out to be positive 30.0 meters. That's called resolving a vector into components. In general, you can't just add two vectors. If I had a vector A is 50 meters at 53.13 degrees, and I had another vector B that's 40 meters at 90 degrees, I can't add those. I can't just go 50 plus 40 or whatever, right? But it turns out you can break each vector up into an X part, a Y part, and a Z part. And the X parts add to all the other X parts, just like positive and negative numbers. Same thing with all the Y parts, same thing with all the Z parts. So this is called resolving a vector into components. Or sometimes they'll just say breaking a vector down into components, and then they'll say resolving is making it back into a magnitude and direction or something. Now, the big trick is, notice I could have another vector. Let's do another one here. And this time, again, this is the x-axis and this is the y-axis. But in fact, I'm going to call this due north, which is a compass heading of 0 degrees. And then this, of course, is east, which is a compass heading of 90 degrees. And this, of course, is a compass heading of 180 degrees, which is south. And this is 270 degrees, which is west. Okay. Now, what vector could I use? Well, I'm going to stick a vector right here. And I'm going to say that this angle phi, that angle phi is, let's say, 30.0 degrees. And let's say that this is 200.0 newtons. So that's a whole nother way I specified a vector. I could say vector B is equal to 200.0 newtons at 30.0 degrees west of north. Everybody see how that's west of north? So I again remember this is a triangle and it clearly has a shadow along the y-axis, and that one looks positive, but it also has a shadow along the x-axis, which I chose to do in red because that looks negative. So now I just write out my sines and cosines again. So let's say the sine of 30.0 degrees is equal to opposite over hypotenuse. So that becomes b sub x over just plain b. So that means b sub x is going to equal, and here's what I mean. I've got to force that negative in there. I'm putting that negative in there because I know it points to the left. So I'm going to take 200.0 newtons times negative times the sine of 30 degrees. Okay. Now, you might recall this, you might not, but basically the 30, 60, 90 triangle, this is 60, this is 30. The 30 is opposite the 1, the 60 is opposite square root of 3, and then this is 2. So the sine of 30 is 1/2. So I get negative 100.0 newtons. That's my x component. Similarly, cosine of 30.0 degrees is equal to adjacent over hypotenuse, which in this case is equal to b sub y over b. So b sub y, I'm forcing this by putting a plus there. That's going to be plus 200.0 newtons times cosine 30.0 degrees. Now I can look at cosine of 30 degrees from the little special triangle I drew up there, and that's √3/2. And I happen to know that's about 0.866. So R, I could say square root of 3 is about 1.73. So the square root of 3/2 is going to cancel out with the 2 and the 200, and it'll be basically around a positive 173. But let me go ahead and use my calculator since I have it and say 200 times the sine of 30. Oh, excuse me, cosine. I did that already. 200 times cosine 30. And that gives me 173.21. Carrying one extra sig fig, of course. And that's newtons as well. So notice how I personally force the signs to be in there. If I had another vector, let's say this guy, and let's say it's 141.4 newtons, and this angle right here is 45 degrees, then I could proceed as follows. I can call this vector C. And what I would do is I'd say the sine of 45 degrees is opposite over hypotenuse. So I can see already that this is going to be a negative component. And this too is going to be a negative component. So this is C sub X, and this is C sub Y. Okay, so sine of 45 is actually going to be CY over 141.4 newtons. And if you remember anything about the sine of 45, it's 1 over the square root of 2. So that's basically going to give you 100. So 141, excuse me, 0.4 times the sine of 45 degrees gives me essentially 100. It's 99.985. So I'm going to call this essentially negative, or actually, let me do it this way. I'm going to take an extra step here. So this means CY is going to be equal to negative 141.4 newtons times the sine of 45 degrees, which is equal to negative 100.0 newtons. Similarly, cosine 45 degrees is adjacent over hypotenuse. The adjacent this time is CX, and the hypotenuse is 141.4 newtons. So that tells me that CX is going to be, again, I force the negative by writing that down, and then I do 141.4 newtons times the cosine of 45 degrees, which gives me, in fact, exactly the same thing, negative 100.0 newtons. Okay. And now I could draw, let's say, one more vector. Let's make this one vector D. And it is, in fact, equal to 300.0 newtons at negative 15.0 degrees. Okay. So in this case, what I see is I have a positive X component, but I definitely have a negative Y component. Okay. So now again, this part right here is 15 degrees. So I'm going to say sine of 15 degrees is equal to adjacent, excuse me, is equal to opposite over hypotenuse. So I'm going to call that dy over 300.0 newtons, what that means is that dy, which I'm forcing to be positive, so I'm going to force that sign right there, and I'm going to do 300 times sine 15, and that's going to give me 77.65. Which is really one extra sig fig, so I'll put the newtons there. Cosine of 15, on the other hand, is adjacent over hypotenuse, so that should be dx. Oh, wait a second, the dy was supposed to be negative. Did anybody catch that, or was I the only one that eventually caught it? I was thinking I had done the x one first. So notice my dy points in the downward y direction. So that should actually be me forcing a negative. Sorry about that. Dx, on the other hand, is definitely a positive. So I get dx, and actually I accidentally erased some things. Dx over 300.0 newtons. That gives me that dx, and now I am forcing the positive because, as I see from the diagram above, dx is clearly in the positive direction, and that's going to be 300 times cosine 15, and that gives me 289.78. newtons. And actually this one really gives me 2 extra sig figs because I've got that big a unit. Okay, so now what I've done between the vector A, the vector C, the vector B, and the vector D is I've now got 4 vectors. Each of them are in a different quadrant. That's sort of what the purpose of me doing the quote unquote world's greatest vector problem was one, I wanted to make sure you understood how you don't use the signs of the angles or any of that kind of stuff. You normally just choose the angle that's easy to figure out and is to the closest axis from your vector, and then you force the signs. So if I want to know what is the resultant R, which equals A plus B plus C plus D, I proceed as follows. I've basically done all the hard work now. So I'll say R sub X is just the sum of all the X components. So A sub X had a positive, and let's assume for a second that everything is newtons. That way they can be added together. So I'm going to say change to newtons, and I'm going to say change to newtons. Obviously, if this was a real problem, you just come up to me and say, Mr. Younger, I can't add those because one's in meters and the other's in newtons, and you'd be absolutely right. That would be my fault. Okay, so right now we're just saying, okay, well, Mr. Younger was giving us an example. I'm going to say change to newtons as well. So I know that the X component of the A vector was A sub X, and we called it positive. So it's positive 30.0. Ooh, I don't want to use those colors. It's positive 30.0 newtons. Now I look at B, I found B had an X component of negative 100.0 newtons. Now I look at C and I see C had an X component of negative 100.0 newtons. And then finally, I look at D and I see that D had a positive 289.78 Newton answer. So I'm going to add all these up. I'll do 30 minus 100 minus 100 plus 289.78. And I get 119.78. Now we knew they were uncharacteristic, so those aren't really sig figs, but that's the x component of our resultant vector. Notice how I used r. That's a typical thing for the sum of any number of vectors we call r. Now I do r sub y the same way. So what I've showed you here is I've showed you how to resolve vectors into components, how to make sure you choose the right sign for them, and then once you have them in components, components just add as long as they're like components, like positive and negative numbers. So a sub y, for instance, is positive 40.0 newtons, again, with my made up part. A b sub y was positive 173.21 newtons. C sub y was negative 100.0 newtons. And then D sub y was negative 77.65 newtons. So I'm going to do 40 plus 173.21 minus 100 minus 77.65. And that gives me positive 35.56 newtons. And it seems like we got no business doing anything beyond the first decimal place with that one. Okay. So now our answer is literally, we can just write R is equal to, here's the neat trick. It turns out, hopefully you learned this in your trig class, but if you didn't, it's not a big deal. It turns out we have defined in mathematics something called unit vectors, and a unit vector always has a little hat on top of it. So it's like a, on my keyboard, it's shift 6. Looks like a little dunce hat. Whenever you have that over a letter, that means that is a unit vector whose length is literally 1 unit, not 1 meter, not 1 coulomb, not 1 Newton, just 1. Okay. So it turns out if you have a unit vector and then you multiply it by the size of the vector you want, then you automatically get the vector you want pointing in the same direction as that unit vector. So in this case, the unit vector pointing in the x direction is called I hat, or if you forget in a pickle, you could just call it x hat. So I can immediately write down that this is 119.8 extra sig fig newtons in the I hat direction. And that decimal has to be there. Plus 35 point, let's do 0.56 newtons in the j hat direction. That is technically the answer. Okay, that is exactly a right answer, assuming I didn't make any careless arithmetic mistakes, which is a huge assumption, by the way, so feel free to look for them. The general rule, though, is if I gave you all the vectors in IJK notation, then you should probably spit them back at me, the answer in IJK notation. If I gave you to them in mixed formats like I did here, then you should wait for the instructions. In this case, I want IJK notation, but I also want magnitude and direction. So what I'm now going to do is show you how to create a vector out of its components. So that's the opposite of resolving a vector in components. So what I have, again, I'm going to draw a coordinate system here. Notice both of my components are positive. So I only need the first quadrant. And this is what I'm putting up here. So the Y component seems to be really, really short, like 35, and the X component seems to be like 120. So I would say my Y component would maybe be this, and then my X component would maybe be that. So this should be approximately 119.78 newtons, and this would be about 35.56 newtons. Now, the way you add vectors when they're tail to tail is you complete the parallelogram. The way I tell my students to do it is I'll grab this 35.56 Newton vector, and let me do this, make this a little neater for you guys. I will grab this 35.56 Newton vector. I will grab it and slide it along the horizontal vector. It's almost like it has like a little loop down here that I'm going to slide, and then the vector will be right here. Similarly, just to make sure, I do the same thing with the horizontal vector, and I slide it until it ends up here. Now, I can take the bottom horizontal vector as it originally was, and the moved A vector, and I see they're now head to tail. So that tells me immediately that my vector R is this guy. So that's my vector R. And this could be the angle, say, alpha. Now, R, I think you'll know, is equal to the square root of 35.56 newtons squared plus 119.78 newtons squared, square root, and that'll give me the magnitude. So let's try that. Let me see, I'm going to square that plus square that, and that gives me 15,611 under the square root. So I'm going to raise that to the 0.5 power, and that's going to give me roughly 124.95 newtons. Hold on a second. This is somebody that doesn't normally call me. Hey, I'm in class right now. Is everything okay? Give you a call. Oh, 620. Oh, excuse me, 640. 640. Sorry. All right, talk to you later. Bye. All right, sorry about that, folks. Yeah, it was no big deal. So that worked out pretty good. So we said that was that. It's a little tricky working out sig figs, but I'll just leave it and assume we got one trig fig there, one sig fig there. Now the angle alpha can be gotten by taking the inverse tangent of 35.56 over 119.78. So I'll take arctan 35.56 divided by 119.78, close parentheses, equals, that gives me 16.53 degrees. So that is how you can build a vector back up into magnitude and direction. Remember, when you open this, you can make it larger like that if you want. I just was trying to fit it in there. These are on my Google Docs, don't forget. So what I'm going to do now is I'm going to say this vector is also equal to R equals 124, might as well call it 125.0 newtons at, and when you say at, if the next number is positive, that means everybody knows you're measuring it counterclockwise from the positive x-axis. If you say at and then the next number is negative, then everybody knows you're measuring it clockwise from the positive x-axis. So in this case, it turned out to be 16.5 degrees. So that too is an answer. Okay. So that's a typical addition of vectors problems. I've shown you a little stuff, like I've shown you some of the different ways you can label them. I made sure I hit each of the quadrants so you'd see that, oh yeah, in the first quadrant, both X and Y are positive, but in the second quadrant, the Y is positive, but the X is negative. In the third quadrant, and by all means, do not memorize this junk. It should be something you can just work out yourself. In the third quadrant, both X and Y are negative. And then in the fourth quadrant, the X is positive, but the Y is negative. Again, what you're wanting to think of is when you draw a vector that's not parallel to one of the axes, you want to take a trip from the tail of the vector along one axis, and then take a trip from the end of that vector parallel to the other axis until you get to the head of the vector. And if you happen to go in two positive directions, then you know both components are positive. If you go in one positive and one negative, then the one that was negative is the negative component, and the one that's positive is the positive component. So that's really how you decide what those vectors, whether those components are positive or negative. Is just, you can imagine walking from the tail of the vector you're talking about to the head, but you're only allowed to either walk along an axis or parallel to an axis. So any questions on that fairly robust vector addition problem? Okay. Well, as I said, this will be on in my Google Docs, so you can go there immediately. What I'm going to do now is give you some other rules about adding vectors. So, and I mentioned a couple of them already, but everything I just did mathematically, you can do graphically. Like if you happen to have AutoCAD, you can draw these things very precisely to the exact angle, to the exact length that you want. And then you can pick up the second vector. For instance, if you want A plus B, you can pick up vector B and put its tail at the head of vector A, and then just draw a vector from the tail of vector A to the head of vector B, and you'll have A plus B. That's how you add vectors that are head to tail. If you have two vectors that are tail to tail, then you complete the parallelogram and draw the vector from the common tail to the diametrically opposed corner. So what does that mean? Let's talk about that a little bit. So let's imagine for a second that I have this vector. That's going to be vector A, say. And let's say I have this vector. That's going to be vector B. Can anybody tell me whether those two vectors are head to tail or tail to tail?
Head to tail?
These are actually, and that, I'm glad you answered that, because I suspected a lot of students don't understand when I say that. So right now we see the heads of the vectors are the little arrows. So right now I've got the tail of the green arrow and the tail of the blue arrow next to each other. So they're called tail to tail. So thank you for answering. And actually that helps because I wonder why sometimes students look at me like I've got like 3 heads or something. But part of it might be because I'm using terms that they're not familiar with and they don't know what it means. So these vectors are tail to tail. If you wish to find A plus B, which is equal to the resultant vector, then you complete the parallelogram. Now, a parallelogram just means opposite sides are parallel. So the way I say that is I don't even think about completing the parallelogram. Remember my rule I told you about vectors? As long as you don't twist them or stretch them or squish them, you can move them around all you want. So what I do is I just move this green vector, 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 until finally I got the green vector now such that its tail is at the head of the B vector. Now I do the same thing with the B vector. I just imagine sliding it along, sliding it along, sliding it along, sliding it along, sliding it along. And then I realized that clearly I didn't draw the green vector long enough. Okay. And this should be roughly the right size. Okay. So now the vector turns out to be from the common tail to the diametrically opposed corner. So this vector is A plus B is equal to R. So tail to tail, complete the parallelogram. Now let's draw another one. Let's say, first off, let me draw a vector A. And second off, let me draw a vector B. Okay. Now, anybody want to take a guess at whether these vectors are head to tail or tail to tail?
Head to tail.
Yes, this is head to tail. Okay. And the reason why is that's a head and that's a tail. Okay. Now, when you add vectors and they're head to tail, it's actually really easy. So I'll say to find, let me separate this line, to find A plus B equals R, you draw from the tail to the head. Notice it's not ambiguous which tail and which head because there's only one tail and one head that are open. So I'm now going to draw a vector from here to here, and that's A plus B is equal to R. So if you took the time to like make up a scale, try to make up a scale where you can take as much of the paper as possible just to fit the vectors in, that'll make you more likely to have a better result. And then you use a straight edge and a good centimeter scale that has nice little markings and a protractor. Then you can usually graphically add vectors like this in such a way that you come within 1 or 2% of the actual answer that you get for more mathematical techniques. So this addition by just drawing scale models works great. It's just too time consuming to do on the test. But if you ever open up Newton's Principia, you'll see that's pretty much what he did, because it was just too much work otherwise. So now I've done the two ways to add two vectors. So when you're adding two vectors that are tail to tail, you complete the parallelogram. However, when you add them and their tail, head to tail, you draw from the loose tail to the loose head. So I might put loose. Loose. Okay. Now there's another branch of, or another mathematical operation. We shall call it addition's friend, subtraction. Okay. So let's do the same thing again. I'm going to draw a vector. This time I'm going to call this one C, and I'm going to call this one D. Okay. What I would like to know is, what is C minus D? Okay. Well, if you remember your rules from algebra, this is why I brought them up earlier. What we know is C minus D is defined to be C plus the opposite of D. And here's a neat little caveat. If this is vector A, let's call this vector X, okay? Then vector 2X is literally the same vector, but twice as long. So I'll go from here to here. If I want vector negative X, then I'm going to draw from here to here. If I want vector 1/2 X, I'm going to draw from here to here. And that's pretty much it. When you multiply a scalar times a vector, if the scalar is bigger than 1, you're going to make it bigger by exactly that factor. If the scalar's smaller than 1 in magnitude, you're going to shrink it by exactly that factor. If the scalar is positive, you're not going to change its direction at all. But if the scalar is negative, you're going to change the direction by adding 180 degrees. Okay. So now that you have that piece of information, and I want to do C minus D, then all I have to do is take my red marker and put this right here, and I'll draw it right below alongside of D, and call this red one negative D. Now, forget about the blue vector for a second. Look at the red one and the green one. Are they head to tail or tail to tail?
Red and green are head to tail.
Exactly. So all you have to do is draw from the loose tail to the loose head. And that's exactly what the answer is. I'm going to draw it in a fabulous black. And it'll be this vector right here. That is C minus D. You might call that S. And just for the record, I'll do this quickly because we're right at time. So I'm going to draw a green vector that is like this and call that vector C. And then I'm going to draw a blue vector like this and call it vector D. And now I'm going to calculate C minus D equals question mark. Okay. But again, C minus D is the same thing as C plus the opposite of D. So I got to just change the direction of D, which I'll add that there and do that. Now that's kind of weird, but remember, we're allowed to move our vectors around anywhere we want. So I'm going to take this and put it right here. And that's negative D. And now I see that, in fact, this time I might go with a fabulous purple. And I'm going to say this vector is C minus D equals S2, say. Okay. So now you've been fully briefed on how you add vectors and how you multiply them by scalars and all that good stuff. Next time we'll work only on basically kinematics related to projectile motion and stuff like that. I will give you as a parting prize, I will write this neat little answer on the bottom that you can play with, but you guys are free to go and I'll just wait for the last person to leave.
Professor?
Who do you want to message?
Nobody, Siri, thank you. Go ahead.
Okay then.
Could I'm sorry, are we going off of MyLab and mastering for due dates or Canvas? Because I noticed that the due dates aren't the same between the
Yes,
two.
I originally state the dates on the modules in Canvas, but sometimes I find out that we run into problems, so I'll only change them on MyLab and mastering. So you can always defer to MyLab and mastering. That's always going to be okay.
Okay, and then I had another question. I noticed I sent you an email about it not too long ago, but I noticed there were a whole bunch of assignments that were labeled as missing that had due dates from like last semester in Canvas. And then I also noticed like you had said that for the faux physics primer and the physics primer that you were going to take the grade from one of them and then not
Right.
have the other one, but it looks like they were graded automatically. And like both of the grades, like I have a 0 for one and then the other one is graded in Canvas.
Yeah, so what I did was I went in and I basically took one column, had most of the students had done it, the other column a few. I took the highest score that you got if you from the two, and I put it in the column that had the most in there, and the other one's going to be erased and not counted at all.
Okay, so it's going to be deleted, but
Yeah, and it just
Okay.
counts as extra credit anyway, so it's only going to add to your grade more or less in a positive way.
okay, I would like because the way that it's being calculated, like as part of the grade in Canvas right now, is it's like bringing my grade down by like 8 or 9 points.
Yeah, I tried to take care of that this morning. So have you seen it since this morning?
I didn't get that. Could you try again?
No, Siri. Bye-bye.
Until we talk again.
So did you see, have you seen it since this morning? Because I might have
Yeah,
fixed it already.
yeah, I had looked at it. I think right before class today, actually.
Okay. Well, I'll check it again, and they should be corrected pretty soon.
Okay.
Okay.
Professor, I had a couple questions too.
Go for it.
Okay, so test one, the online test that's online, when will that open?
I should have it up today or tomorrow, probably tomorrow.
Okay. Okay, and then will that be on Canvas or mastering? Where will we be able to complete it?
It's on Canvas, and you get at least, I normally give you at least 3 attempts, and only your highest counts.
Okay. And then on mastering, I noticed that this Sunday, the 5th, we have both chapters 3 and 4 homework due. Is that like going to stay the same? Because I noticed that a lot of the
3 will be due. I'm going to push 4 back since you have a test.
Okay.
So bare minimum, I might even push 3 back to Wednesday, but bare minimum, I'm going to push 4 back.
Okay. And then my last question, it's actually more of a comment. So I noticed that over the weekend that you were putting in stuff like PT, like practice tests, like 1, 2, and 3 for all the chapters. And I appreciate that. However, I noticed that the due dates are in September and October of last year. Therefore, they are locked and we cannot access them.
Yes, I tried to put for the first 4 chapters, I tried to get those done. I might have gotten one class done and not the other, but that's on my list to do. And
all right,
so they'll
thank
all
you.
be available to you, and they don't count for you or against you. I mean, I can tell, like, it'll tell me how much time you spent on them, but I won't be able to see any grades or anything like that. I'm just putting them there specifically because students have said they would like to have just a plethora of chapter 1 problems that they could just solve whenever they had a moment. So I made that area.
Okay, so sometime during this week, the due dates will be changed. All right, thank you.
Yeah, no problem. Thanks, Alex. Anybody
One
else have any
more-
questions? I just
Yeah.
wrote a position vector for projectile motion. And then I took the derivative of the position vector and got the velocity vector. And then I took the derivative of the velocity vector and got the acceleration vector. Just something you can think about and actually use if you wanted to start doing any projectile motion problems. The bigger thing from chapter 3 right now is make sure you can do your addition of vectors. I'll be putting some problems up on, well, there's a ton of problems already on my YouTube channel, but I've put more in module 2 and module 3 than when module 2 and module 3 opened. I don't think I added any more to 1, but you might want to go back and look. There's plenty of examples in there. Okay.
All right. I have one more question on behalf of another student. They wanted to
Go for
know if they could still turn in the physics primer and introduction to mastering physics.
If the due date's passed, I won't be able to just because of all the junk I had to do. So yeah, it's I think the due date is passed on both of those, so they probably can't. Tell them don't worry though, there will be plenty of extra opportunities for you to get extra credit. Anybody else? All right, well, let me stop sharing here.
I actually have a question.
Yes.
May I share my screen?
Let me set it so you can, and then I will say yeah. Yeah, you should be able to now.
Okay.
Hey, Professor, what is going to be the time limit for the test?
It's usually not very long. Like, I think I'd normally do like 30 minutes for 14 problems or something like that. So it's expecting you to do them kind of quick. But the reason being is I want you to be able to look up a question if there's one that you don't know how to do. I really don't want you looking up any more than that. So, I mean, you can if you can fit the time in, but if you are doing that, that's going to bite you in the rear come midterm.
Okay, here's my
I'll give you
question.
some actual data when I make it up because I'm not remembering off the top of my head exactly how I did it. So when I open up a new test and I look at my old test, I'll have a better idea. So I'll send out a announcement to everybody and let them know roughly. So this is what you're talking about, Kamna?
Okay, no, I wasn't the one that was talking about this one, but I know what you're talking about. Somebody asked about this.
Yeah, see, this is crazy because
But this, this is not the question I have. My question is, where do I go to take the, do the homeworks and the tests in here?
Click over on the left-hand side where it says modules. That's where I want my students to go everywhere. So first thing, go to modules, scroll down. Right there is where all the practice ones are. And right there is where the practice test. And right in between that and week 1 will be where the online test is.
Okay, so add the homework in here because I don't see them.
The homework is in the individual modules. So scroll down to week 1. And see the homeworks that says homework conceptual 1 and then homework 1. And the same thing with week 2. That's the way I expect all my students to be using Canvas, but I've discovered that they clearly don't do it that way necessarily.
Okay. I've been doing it on my lab.
That's
my
fine.
screen.
Yeah.
Okay.
Again, guys, I want to mention this to you. I've mentioned it a couple times. I want to make sure I mention it again. Hey, if you guys are hiding from somebody or don't want your name or whatever on the internet, please let me know. I'll do what I have to try to blur it and all that good stuff. Sometimes you have people that are, escaping abusive relationships. Sometimes you have people that just don't want anybody to know what classes they're taking. So if any of y'all have any problems with that, please let me know by email and writing, because otherwise they're just going up in YouTube, and like right now you just popped your name up there and someone saw your name. They actually saw a little bit of your grades, but I didn't do that, so I'm not the one.
Okay. I get it.
I mean, your grades
So-
are good, so it shouldn't matter, but I just want to warn everybody about that.
So how do I get to the, I wanted to ask that one.
How do you
Okay.
get to the My Lab and Mastering?
Exactly, yes.
Okay, go back to that window you were just in, or
Okay.
click on Canvas.
Right
See
here.
the My Lab and Mastering right below Zoom and right above modules.
Come on.
That takes you there. And if you click Open My Lab and Mastering, that big yellow button, that'll take you where you can see your calendar as well as your ebook. See the Pearson
Alright.
e-text on the left?
Okay. All right. So
I'm glad you asked this because I suspect there was other students that didn't know either. So thank you.
yeah, but the thing here, it will still ask me to purchase. I already purchased it out of here.
Right. It shouldn't have to now. If you run into any problems where it's doing that, then contact Pearson. Look for contact us and make sure. And if you can't get a response, then let me know and I'll get my own personal sales rep on it.
All right. Thank you.
No problem. Anyone else?
I think they all go.
I think it's only you and I. Well, you have a good one, sir. I hope
All right.
your questions okay.
All right. Yeah. Bye-bye. Yeah. Everything is okay. Thank you.
All right. Have a good one. Bye-bye.
Bye-bye.
So bye-bye. Bye. See ya.